All right, in the last lesson, we looked at functions, and remember what a function was? It's a special kind of relation. And the thing about functions that are special is that if you give them an x value, they'll only produce a maximum of one y value. Okay, so remember in the notes what we went through, what we looked at was a few different varieties, and I'll just pull them back up again just to jog your memory. So this graph here was a function because when I fed it an x value, it produced a unique or one y value, one y value, one y value. X value gave us a y value, x value gave us a y value. This one was not a function because when I gave it 8, it produced this y value and this y value. So that's not a function, okay? And remember that what we were doing was essentially doing what's called the vertical line test, okay? And the vertical line test is if I draw a vertical line through the graph, do I hit only one x value, only one y value given an x? So today what we're going to do is extend our understanding of functions and look at this thing called a one-to-one function. So one-to-one functions and implied domains is our topic for today. So again, this goes through function is a special kind of relation. And we know that if a horizontal line is drawn anywhere on a graph of a function and it intersects only once, then what happens is we call this a one-to-one function. Now, what does that mean? Okay, so the vertical line test tests whether it's a function or not. The horizontal line test tests whether the function is one-to-one. So this one here, I'm going to say is not 1, 2, 1. Why not? Well, again, if I draw a horizontal line through that, I'm going to hit this value and this value, okay? And that's a problem. It's still a function, I'm not denying that, but it's not a one-to-one function because what that means is there's two x values here, this x value and this x value here, that will produce exactly the same y value, okay? Now, this line here, if I draw a horizontal line anywhere through it, I'm only going to hit a maximum of one y value, okay? So therefore, what we say is this is 1, 2, 1. Okay, it's a function and it is a one-to-one function. Now, this one here is not 1, 2, 1. And what these guys have done is produce this horizontal line here, which if you draw a horizontal line through the horizontal line, you'll hit infinitely many y values given a value for x. So this value of x produces 5 and this value of x produces 5, okay? So we say that that's not a one-to-one function. What about this one here? Okay, well, again, what happens, even if I go through the stationary point of inflection right there, I'm only going to hit a maximum of one y value. So this is 1, 2, 1. This one here, can quickly draw the horizontal line test and note that for these two values of x, it produces exactly the same value of y. So we say that this is not 1, 2, 1. Okay, so let's start to apply it a little bit more. So we've got a function here, x squared take 4x plus 7. And what we want to do is write the domain. Okay, so the domain is x is an element of all real numbers, okay, because it's a parabola. Now, what we want to do is create a new function that is one-to-one based on this, okay? Now, because it's a parabola, let's just quickly sketch it. So it's going to be, so to sketch it, I'm going to complete the square. So y equals x squared take 4x plus 2 squared take 4 plus 7. Y equals x take 2 all squared plus 3. So there's 2 and there's 3. That's the turning point and it's an upright parabola. Okay, so it's a function, that's for sure, because for any value of x, it produces a maximum of 1y, but it's not one-to-one because if I do that horizontal line test, you can see here that I'm going to hit this y value and this y value for these two values of x. Okay, so it's not one-to-one. So what they want us to do is create a new function that is one-to-one based on it. Try it out and see. So can you make a new one? So I'm going to call this g of x, okay? And what I'm going to do is state my function, which is x squared take 4x plus 7. And you might be thinking, oh, Mr. Miller, it's exactly the same function. But hang on a minute, where x is an element. And what I'm going to do is restrict the domain. So my new function based on this, where x is an element of, and I'm going to say, I'm going to let you do it from negative infinity all the way up to the turning point, inclusive of that. And what that's going to do is only accept this part of it. Okay, it's going to chop out this part of it, which basically means that I'm going to be one-to-one. It's only this part here. Okay, so if I do the horizontal line test, and now I'm only going to hit a maximum of one y value given any value of x. There's another answer you can give to this. H of x equals x squared take 4x plus 7, where x is an element of, let's start at 2 and go to positive infinity. And what that essentially will do is just take the other side of this. So it'll cancel out this part and accept that part. There's infinitely many answers to this. Okay, you could say h p of x equals x squared take 4x plus 7, where x is an element, excuse me, and we're going to start it at 3 to 15. Okay, that's only going to be this little portion of it, all right, and that will be a one-to-one function. If the domain of this function here is classic exam question here. All right, so we've got a domain of this, okay, for this particular function. What's the largest value of p? So it is one-to-one. Right, so again, the quickest way to do this problem, I think, is to complete the square. I'm going to say y equals x squared plus 6x. What are we going to do? Halve it, square it, subtract it. Okay, so it's going to be negative 3, negative 12. Right, and what we want to do is restrict it, so the largest value. So it's going to go from negative infinity, so it's coming along this in this direction here, negative infinity, all the way up to which value here? Well, it's going to be to the turning point. So it's going to be where x is an element of, whoops, negative infinity up to negative 3, including that value. Therefore, p is equal to negative 3. All right, so do the bookwork. Now, you don't really know why it's important to know what a one-to-one function is, but we're going to use it. We're going to use it on Thursday or Friday, whenever we have class next, because what I'll go on to teach you about is to inverse a function. The function in the first place has to be one-to-one. So we need to be able to spot a one-to-one function. We need to know how to restrict a domain to make a function one-to-one. All right, in addition to that, what we're going to do is work through just applying some function notation and some modeling. So what I'm going to do where possible is to use some calculator on this stuff here. Okay, so we've got an example here. The volume of a sphere of radius r is determined by this function. Take the practical domain of the function v and find v10. Okay, so the practical domain. So let's just have a look at this function. So I'm going to go into graph and table, and we're going to graph it. So that is, actually, let's not do that. Let's go into main and let's define our function. Okay, so recall that to define a function, we go to math 3 and define f brackets x equals shift divide for fraction, 4 on 3, shift 0 for pi, and this is r to the power of 3, but I've used the variable x in my definition, so x power 3. Okay, so we can do f of 10 first of all. So that's easy. So we're going to say that this is F10. Whoops, that's a big mistake there. Be careful. V10, use the notation that you've used in the question rather than what you've used on the calculator, equals 400 pi on 3. Noting that we don't round this number. We don't do approximations. And the domain, it's going to be for R is an element of, well, it's got to have a radius. So we're going to start at 0 through to, well, this radius can be as big in theory as you want. Okay, so if you want the radius to be the distance from, like Earth to Pluto, then that can be your radius. Okay, so without getting too philosophical about infinity and all that sort of stuff, we're just going to say where R is an element of all real numbers. Now let's just see how that works. So I'm going to go into menu, graph and table, and once you've got your function defined, we can actually go ahead and say, hey, can you just graph f of x for me rather than retyping the whole thing? All right, so there it is there. As x or the radius increases, so too does the volume. And in theory, the volume can be to infinity. I know it can't, like in volume and water in space and all that sort of stuff, but like, let's not get into that. In theory, it could be to positive infinity. All right, and the area of a rectangle A can be determined by the function here with the rule blah, blah, blah. State the practical domain of the function A and find 3. That should be A of 3. Okay, so just correct your notes. Okay, so again, because I think we want you to, we're going to use our calcs and we're going to run a define. So define fx equals, and our function is negative x squared plus 9x take 14. All right, so now let's do f of 3. And we're going to say that a of 3 is equal to 4. And what's its practical domain? Well, we're talking about area of a rectangle. Okay, so let's go back and have a look at it. So there it is there. And what happens is as x increases, so starting at 2 all the way to 7, it looks like, we're going to get a positive area, okay? So it's when a of x greater than 0. So let's have a look. We're going to say, so it's going to be when a of x greater than 0. So it's when negative x squared plus 9x take 14 is greater than 0. So let's factorize that. So I'm going to go x squared take 9x plus 14 less than 0. I've divided both sides by -1, which means I need to flip the inequality. Okay, 14 is going to be 7, 2, neg x, x take 7, x take 2 less than 0, 7, 2, upright. When it's less than 0, x is an element of between 2 and 7 inclusive. Okay, so that's the area that will produce, well, that's the values of x that will produce a positive area. All right. Classic simultaneous problem. So what we're going to do, we know that f of 1 equals 7, f of 5 equals 19. So we're going to go 19 equals a 5a plus b is my first equation, and 7 equals, so I'm substituting 5 into it, and now I'm substituting 1 into it, a plus b. This is 1, this is 2. We're going to do 1, take 2 to eliminate the b's, and I'm going to get 12 equals 4a, a equals 3, b is going to equal, 4. So my function is f of x equals 3x plus 4, and the graph will be y-intercept of 4, x-intercept of -4 on 3 through those points there. I can't do that. I've got a stylus not on the screen here. I'm pointing at a pad that I'm typing on. So that's got to go through there. And don't forget -4 on 3, 0 and 0, 4. Yeah, so this bruiser was written by Ms. Cowan a few years ago. So let's have a look at it. We've got the standard 120 meters of timber used to construct a rectangular paddock. It's got an opening of 4 meters along one of the sides where a metal gate would be fitted. So we've got a metal gate here, presumably to keep the cows in the paddock or something like that. If the width of the paddock is x and the length is y, right, what we have to do is express y in terms of x. So that's going to be x, this side is going to be y take 4. So what are we going to do? We've got x plus y take 4 equals 120. 2x plus 2y equals 124. 2y equals 124, take 2x. Y is equal to 62, take x. Okay, area is length by width. Area equals x times y. We've got x, we multiply it by y, which we just found out is 62 take x, which equals, area equals 62x, take away x squared as required. State the domain of A and hence write an area function. Okay, so let's write the area function. A of x equals 62x take x squared, where x is an element of. Now, what values of x are we going to allow? All right, so let's have a look at the graph. Okay, so edit, clear all, and let's go and graph it. That's going to be 62 take x, 62x take away x squared. And what I can quickly see is it's going to have intercepts. So max, let's go 200. Intercept is going to be at 62, so roughly 70. Let's see if I can spot it. Right, so you can see here that we're going to get these two x-intercepts here, okay? So are we allowed to then just say where x is an element between, and don't write this down just yet because we'll discuss it, between 0 and 62, okay? Because that's when it seems to be producing a positive area, okay? Well, not really, okay? Now, why? All right, so we're saying that x can be anywhere between 0 and 62, okay? So if we say that as x increases, let's have a look at the values of y that are acceptable, okay? So what we know is that y take 4 must be greater than 0. It has to be, okay? Now, what do we know about y? Well, we know that y is 62 take x, okay? So let's just solve this one here. 62 take x take 4 has to be greater than 0, which means we've got negative x plus 52 has to be greater than 0. Negative x has to be greater than negative 52. X has to be less than, whoops, I think I've miscalculated, 58. Oh dear. Worst 8 ever. x has to be less than 58. So it seems to suggest that even though our calc shows us that we've got x-intercepts at 0 and 62, that this constraint of the gate causes some ramifications for the values of y. Okay, so note that this comes around when we chop out parts of it, that it's not perfectly symmetrical in terms of its rectangle or not. Okay, so actually this is not the correct domain. What we're going to do is say that x is an element. You can jam in 0 if you want, and you can go all the way up to 58, not inclusive, because if you go higher than 58, for example, if you want to put 59 in here, what that's going to do is this side here expressed in terms of x, let's have a look. We're going to write it as 62 take x take 4. So I've put this value of y in here, and if you let x equal 59, 62 take 59 take 4 means that this is going to be 3 take 4, which equals -1, and pretty hopeless paddock if it's got an area or a length of -1. Okay, so let's graph it. So we're going to say that that's going to be annoying. So starting at 0 all the way up to 58. Now it finishes at 62. So that's going to be 31 as the midpoint. So a graph is going to go up to the midpoint, 31, hit 54, and terminate there. And we're not allowed to use 54 itself, so I'll just redo that. Open circle. All right, so we need to list the key features. So 31 needs to be listed. X-intercept is 0, 0. And this one here is going to be 58, comma. Let's quickly do that. Um, 62 take x, take, I did it again. So we're going to do f of 58, 232. Let's get the turning point. The turning point is going to be at 31. So I'm going to do f of 31. 961, excuse the scale, it's way off. 31, 961. Okay, so this is area versus values of x. So state the maximum area which can be enclosed by the fencing and the gate. Well, the maximum area is going to be this one here, which is 961 meters squared, I presume. Okay, so your homework for this particular exercise is going to be 5F and 5H. Okay, so 5F, 5H on top of the questions on one-to-one functions, which is 5D. So a bit of work there. That's going to be quick. This one will take a little longer. Use your calcs for the modelling questions as well, girls, just to get your skill and practice up on those.